Okay, so we also said that the iridescent colors on butterflies was due to some kind of interference effect. So if you touch a butterfly, you get this dust on your hands. And what that dust is actually the scales on the wings of the butterfly. So here you can see an image from a scanning electron microscope of the wings of the butterfly and the scales on it. If we zoom in a little bit more, you can see that the scales have this very fine structure. There's these bars here. They're something like 2 microns apart. Okay, now remembering that a wavelength of light is something like half a micron. So what happens is the light comes from some source. You're over here at a place of observation. The light comes down and it reflects off of these ridges. Of course, it also reflects off the other ridges. So this would be like those cases we did with 2 paths. But there's not just 2 paths in this case. There could be multiple paths depending on how many of these ridges the light strikes. You could have many, there might be 100. Now we didn't do the math for that, but I can show you the results. So this is the one we already did, the n equals 2 cases in blue. So that's when there's just 2 reflections. So the red line here is 3. Okay, so you can see that we have, this is the interesting part, is I'm not changing the distance between the ridges. Those are always the same distance as just 2. Okay, but we're adding more and more ridges. So you can see that we still have these maximum in the same place. It's just that they're a bit sharper now. When there's 2, we have a width like this, and when there's 3, it's more narrow. You'll also notice that there's a little lump here in the middle. Now if we go to 4 of those bars, it gets even more narrow. Again, I'm showing the 2 case there for reference. If you go to 5 bars, it gets narrower, of course. 6, 7, 8, it keeps getting more narrow. And these side lumps here keep getting smaller. What I'm not showing is, I've made it look like it's just the same height as 2, but it's actually getting taller also. So it's getting brighter at this central spot and dimmer out here. Okay, if we go to 100, you end up with just a spike. So this would be massively bright in comparison if we add it to scale. And notice that it's essentially just flat out here. Okay, so if we think about what this means, it means that this pattern and the intensity of light is really focused on just these spots. It's not oscillating up and down with intensity. It's either here or there and nothing in between. Okay, so this is just for fun. This is, we've zoomed in on just this region here around one of the spikes. And I've graphed it in green. And on top of it, I've graphed this sinc squared function, which is, if you remember, what we get for a single slit. And the interesting thing is that in this spot here, for the single slit, we would have had this. But what we have now, is we've replaced A with n times the distance between the bars. So if we think about that, we have this sequence of bars on the butterfly scale. They're each a distance d apart. That was the thing we were holding constant. N is the number of these. So this total distance here is n times d. So the overall, these spikes have the pattern of a single slit, which is equal to the total illuminated area of all those slits. So it's this distance here is what is A. So that's just a nice coincidence. So if you need to ever know how wide this thing is, you can just think, I'm going to treat it as a single slit with this width. And then you can calculate it. Okay, so the critical thing here is we're not really adding any new math. Okay, the details of this pattern, I could write out the function. It's not really this kind of weird lumpy thing. It's not so complicated. We could write it out, but we're not actually going to do anything with it, so I won't. So the important thing to remember is that if you compare it with the double slit pattern, which you do know, the maximums occur in the same place. Okay, so that's all you need to know for this sequence of reflections. By the way, this has a name. It's called diffraction grating. People manufacture them to do this kind of thing, but butterflies do it too. So any repeated pattern like this that can reflect the light. So the key is that you get these spikes at the center at the same location as for a double slit. So if we just add 2 with that same spacing, you would get maximums. If you add more, it doesn't change the location of the maximums, it just makes them sharper. So that's the main takeaway for today. The same thing is actually in effect here. Maybe you've seen these like iridescent beetles or flies have the same effect. It ends up being the same thing. If you also look very closely at these, they have a very detailed structure on it, these repeating patterns that has the same sort of effect of having repeated reflections in certain directions. So you have this periodic structure which leads to making effectively a diffraction grating. This one's more complicated, it's sort of in 2 dimensions at once.